Hi everyone, welcome back to the channel GVM Success Path. Today we are into an important result from coding theory, the Gilbert Varshamov bond. Imagine we want to send data like messages or files over a noisy channel. We want to make sure errors can be detected and corrected. That's where error coding, error correcting codes come in. But here's the question: how do we know if a good code exists for our needs? The Gilbert Varshamov bound gives us the answer. Now, let's see what is this Gilbert Varshamov bound is about. It is a rule that helps us to know whether good error correcting code exists even if we don't build it. Now, let's see what kind of code it is. A linear code of length n, that is how long each message is, and the dimension k, that is how much actual information it holds, and the minimum distance d, how many errors it can detect or correct, and over a field fq, finite field, like binary is equal to 2 symbols, or q is equal to 3 or 4, etc. Now let's see what does the theorem say. This is the theorem inequality. Now let's see what does the theorem say. If the number of allowed error patterns is less than the number of the possible syndromes, that is error checks, then there must exist a linear code that can detect or correct those errors. In math terms, q power nk is greater than or equal to summation I is equal to 1 to d minus 2 n minus 1 I q minus 1 power I, where q power n minus k is the how many ways we can check for errors. How many ways we can check for errors. We can check for errors. These are called syndromes. Syndromes. And then the sum is how many error patterns are there with less than d mistake. How many error patterns with less than d mistakes. If the check power is stronger than the number of error possibilities, we know a code exists that can correct up to d minus 1 errors. If the check power is stronger than the number of error possibilities, we know a code exists that can correct up to d minus 1 errors. Till now, we have seen about what is this bound is about, and the inequality and the terms in the inequality. Now, let's see the proof from the basic itself. First, we need to know about linear codes. A linear n comma k code over a finite field fq is the k-dimensional subspace of finite field fq to the n. That is, the code has length n and there are up to q power k code words, and this can be described as either generator matrix G of size k cross n or parity check matrix H of size n minus k cross n. Next, we see about minimum distance. Minimum distance d of a code is the minimum number of positions in which any two distinct code words differ. That is, it tells us how many errors that can be detect and correct. Actually can detect up to d minus 1 errors and can correct up to d minus 1 by 2 errors. Let's see the statement of the theorem. Let q be the prime power. This q is the prime power, the size of the field, and n, k, d be the integers. If the inequality holds, that is, which inequality, q power n minus k is greater than d minus summation I is equal to 1 to d minus 2 n minus 1 I q minus 1 power I, then there exists a linear n comma k code over the field finite field fq with minimum distance greater than or equal to d. That is, as I explained before, if the number of syndromes is greater than the number of error vectors, then we can find a code with minimum distance less than at least d. First and foremostly, we are aiming to construct a parity check matrix H of size n minus k cross n such that the resulting code has minimum distance at least d. So first start constructing H column by column. First we are constructing H column by column. Each column is a vector in FQ to the n minus k. We choose them one by one, ensuring that no d minus 1 column are linearly independent. But this construction of parity check matrix is hard since there are many bad combinations. That is, if d minus 1 columns are linearly dependent, then the code could have less than distance d. So, avoiding these bad choices, to avoid these bad choices at each step, count how many bad vectors would create a bad combinations, that is dependent with d minus 2 previous columns. So the number of bad choices is at most summation I is equal to 0 to d minus 2 j minus 1 I q minus 1 power I, where j minus 1 is the number of columns chosen so far. So, how do we know that there is a good vector to choose? If the total number of vectors available, if the total number of vectors available is q power n minus k is greater than all possible bad choices across n steps, then we can always find such a good vector. So the final result is this construction, that is construction of this parity check matrix, guarantees the code of length n, dimension k and minimum distance greater than d. So if the inequality in the theorem is satisfied, such a code must exist. So, this Gilbert Varshamov bound ensures the existence of code with a given n, k, d if the syndrome space is large enough compared to the error vectors. Why this theorem matters? This theorem is powerful because it helps us plan our codes and gives us existence. Even if we don't construct the code, it sets us a benchmark for the code designers. Also, it is especially useful in theoretical research, cryptography, and communication systems. I have explained this Gilbert-Varshamov bound theorem as in this picture in the simple terms. So that's the Gilbert-Varshamov bound theorem. If this helped you, leave a like and subscribe for more math content and comment below if you want a PDF notes. Existence is par. Plan smart with Gilbert Varshamov bound. Watch our next video on linear codes and Hamming bounds. Thank you. See you in the next video.